Well, hello, it's Friday evening, and this is my second video of Friday evening, and we kind of talked about this topic on Zoom earlier, but this is section 15.3, and it's using a double integral to find area. So what I tried to remind you of is back in general math, we talked about this in the Zoom session on Thursday. Let me make it bigger so you can see things better. And the other good news is I'm just using my wife's completed note copy for all of this. So you'll have typing and you'll have handwriting you can read instead of mine. Lucky you. Alright, so the idea is that when you find the volume of any kind of solid, I don't care if it's a rectangular solid like this, or it's a cylinder like this, if you can find the area of the base, which in this case is this thing, stop, then all you have to do is multiply it by the height. Okay, and so that's what this formula is referring to right here. The volume is equal to the area of the base times the height. That's what the capital B is. Now, the idea is that when you do a double integral with a surface, and I don't think I need these pictures anymore. When you do a double integral with a surface, and they write it, a lot of times they write it like this. No, they put it here, I think, and they have some f of x comma y. So they are identifying what amounts to a double integral, and what you're finding is the volume. And this is your surface right here that is above some region that is cut out by some function. Call it G1 and G2 or G2 and G1, it really doesn't matter. And then some boundaries where you have A and B. Well, what's happening then is this is your base. And whatever this value that you get by substituting all of those numbers in that are here, that's going to be your height. So if your height is equal to 1, the answer that you get when you do the general math formula is the same number as what you'd get if you did the volume. In other words, if you had an area of the base that's 10 square units and you multiply it by 1, you end up with 10 cubic units. But when you think about it, because of the 1, that 10 cubic units is going to be the same number as when you talk about the area of the base. It's going to be the same number. So what all this scribbling is supposed to represent here, and I'm going to erase a bunch of it, is that if you want to find the area using a double integral, then all you have to have here is a 1 as your function. If that's a 1, then you're finding a number that's really a volume, but it's going to be the same number as the area of the base. So that's what we're going to talk about now in all of this. Well, look at that, how wonderfully typed it was right there. Okay, so if your area is 28 square inches and you have a height of 1, you have 28 cubic inches. That's what this is showing. It gives you the same silly number either way. You just have to recognize that if I have a 1 here, I can use that to help me set up and find the area of the regions that are bounded by the double integrals, the iterated integral. Alright, so let's see. She likes to write some notations to herself sometimes. Alright, so if the function is equal to 1, the volume and area have the same numerical quantity, not the same units. And that's what I've been trying to say back up here. Back up here somewhere. There it is. I don't want to erase it. Alright, that ought to be a fun thing for you to watch later. Alright, so it's what is being stated down here. So anyway, if you see this particular formula, and it's a volume formula, and you evaluate the iterated integral. The double integral is the fancy way of iterated integrals, and we end up with 8/3, then you can remember that, yes, technically this is a volume, but this volume has the same exact number as what the area of the base is, just like we did back in Calc 1. And again, this ought to be familiar to you if you use a vertical representative rectangle. This is your dx, this is your slide, back up here. That's your thickness. The slide, I said it wrong, the dx is your thickness. This is your slide. It's going to have to slide from a 0 to a 2 to finish that job. You can see it better if I don't draw all over it. And so that's what those boundaries are referring to, is the shape that you're seeing right here. And this is going to be the area of the shape. That number is going to be the same number as if you were doing the volume of that and your function was a 1. Alright, so if you understand general math, then you know what we're doing here. You just have to be careful when you set it up, because I'm going to ask you a question where it's going to say, express the region's area as an iterated double integral, and I may not make you evaluate it, but you got to set it up. So the process is going to be, you have to graph these things, and oh my gosh, Pasquale, you have to graph a conic section that is a parabola that opens to the right. And you need to recognize that at some point in time. Now, if you don't recognize that, well, this is what I would have said for the first one. The x equals y squared minus 1. That's like a y squared equals x plus 1. I don't think you can see that color very well, so I'll do a different color. And so that's what you graph. It's going to be a parabola that opens to the right, and its vertex is going to shift to the left 1. So the vertex is at -1, 0. And that's what the graph of, let me do it with a very light color. That's what the graph of this one would be. Alright, and the same thing would happen if you're talking about the other equation. Those of you that are conic section insufficient, I can't think of the word I was going to use. But if you manipulated that one, that's 2y is equal to x plus 2. Or that's 2y squared is equal to that. So y squared is equal to 1/2 times x plus 2. So it changes the shape a little bit. But it doesn't change the overall shape, meaning it's still going to be going to the right. It's going to shift to the left 2. And again, let me get a different color so you can kind of see it. It's going to be this shape that you see right here. Alright, let me get rid of that because it looks pretty bad. Okay, so the next order of business then is for you to figure out how to set it up. And if you decided to use a vertical representative rectangle, that would be a bad choice because you'd have 3 different boundaries that you'd have to deal with, so don't do that. The best choice, and I need to stick with red here, the best choice is to do this horizontal one, which means your thickness is dy, and then you have to do right and left. And so the right function is the orange one, the first one we talked about, this one. And the second function is going to be the one that's to the left, and that's the 2y squared minus 2. And then how far would this thing have to slide to cover that entire area? It's going to have to go from -1 to 1. And there's your setup. And again, I'm telling you, I'm going to do a lot of problems where we just worry about the setup. Alright, so we have another question that's doing the same thing. I probably should slow down here a second. Let you look at that. Alright, so let's look at another example and move this up. So you have we're supposed to do the region's area as an iterated double integral and evaluate the integral. Okay, the boundaries are the curve y equals e to the x and these 3 lines right here. And so when you look at that, hopefully you remember how to graph. You're going to have, let's highlight it again. The e to the x is going to be this one. The x equals 0, the x equals the natural log of 2, and the y equals 0. The representative rectangle is going to be better if we do a vertical one, because if you did horizontal, let me show you quickly that you'd have a change in boundaries. You'd have the, you'd have the e to the x on the left side of the top one, and then you'd have the line, and then you'd have the two lines there. Alright, so the correct version, the easiest version would be to do that vertical one, which means then you have your thickness is dx, and how far this thing will slide then is going to be from 0 to the natural log of 2. So here's the setup. So again, oops, there's the setup. And again, it's upper minus lower for that first set of boundaries right there. Okay? You're going to get the quick version of these things, by golly. Alright, counting to 3. Alright, same question. Find area. Oh yeah, whoops, I forgot to make a big deal about something. Because we were finding area, we had to use a 1 right here. If you use any other function, it's not an area. So it's got to be a 1. I'm sorry I didn't say that. I'll say it again right now. This has to be a 1, and if you don't bother to write it, it's okay because it's understood to be a coefficient of 1. So again, what you're going to need to be able to do, all of you graphing people that don't like to graph, is you need to be able to graph and find intersection points and those sorts of things. Which I realize right now, I didn't go back over that very well, but you can look at this intersection point calculation and you can see what we did for that. And now when we do the intersection point, it's just a matter of doing a quadratic and being able to factor that. Okay, so you have two different shapes. You have the line right here, and you have the quadratic right here. And so when you look at that, the best choice is to do a horizontal representative rectangle, because if you didn't, if you did vertical, you'd have a change in boundaries right there. It would be the parabola and the line, and then the parabola and the bottom of the parabola, the top and the bottom. So the correct way to set that up would be to make sure you did a horizontal representative rectangle, which means then you have a thickness that's dy. Thickness is dy, and that's what goes on the outside. And then you have right minus left. And the right function is the line, and the left function is the parabola. And you have to have it solved for x in terms of y, because if I haven't emphasized this enough other times, I'll do it right now. This letter and these letters can never match. They have to be different. Okay? And these these things have to be numbers. If you have letters there, you've set it up incorrectly. You're never going to be able to evaluate that double integral. You're never going to get a number. So let me erase all these beautiful orange marks here. Okay, so here it is solved. I don't need to do anything else actually more I think about it, because most of the time I'm just going to ask you to set it up. Okay, moving on. Count to 3. Count to 3 again. Alright, in this particular problem, I probably would never give you one of these, to be honest with you, but here it is. You're doing an area again, and you've got this weird set of shapes, okay? You've got it given by these curves. Actually, it's the double integrals that are given to you. So you have to translate each of the two shapes. Let me zoom in for that a little bit. And so in dx or dy and dx means you have vertical representative rectangles. And the way the first one is set up, you have the upper boundary is the square root function. The lower boundary is 0. That's high minus low. high minus low, and then it has to slide from 0 to 4. And because this is such a weird monstrosity as a shape, you've got to then look at this equation, and that's going to give you this portion. That's going to be high minus low, which is the x-axis and the parabola. And if you're just doing that region from 0 to 2, then that's what your boundaries here are going to be. So basically what you are practicing here, as far as I'm concerned, is can you translate this kind of expression where you have two of them, and there's too many arrows all over the place. Oh no! And there it is again. Good job. Maybe I shouldn't erase. I've discovered how to fix my mistakes when I delete things. That's good news. So if you want to evaluate it, here it is. I'm not going to make you evaluate it, though, most of the time. And I don't know that I'll ever give you one where I give you two pieces like that. All right, I think that's actually the last one. Let me check. So let me zoom out so that you can see it all. I'm going to count to 3. And there we go. We are done. Hot diggity. Next one won't be so fast.